Okay, so this is the prep video for section 3.5, implicit differentiation. This is a concept that it would behoove you to spend a little time making sure that you kind of get the basics, because once you have the basics in hand, then the rest of it goes so much more smoothly. So this is going to use chain rule as part of it, but we also, before we get there, we need to define what implicit means. So first let's define what explicit means. So an explicitly defined function is one where the dependent variable on the one side by itself equal to some explicit, some definition that you can write down. So an example would be y equals x squared plus 4. I can write that as y equals a function of x, and that function is x squared plus 4. Okay? Another example is like if we were looking at cost, 10t plus 1,000. I can write that as c of t, a function of t, expressly written as 10t plus 1,000. So an explicit function is where your dependent variable is an explicit function. It's directly written in terms of the dependent variable. Okay, so let's look at implicit functions. An implicitly defined function may or may not be able to be written that way, but it is at least not written that way to begin with. So here's one. I don't know if you remember back to pre-calc or algebra when you were looking at solving simultaneous equations, two equations and two unknowns, and we would want to write the equation in standard form. This is an equation in standard form, not slope-intercept form, but standard form. And so here we could clearly, this is not y equals something. So y is defined, but not by itself on one side. This could, of course, we could solve for y and get to an explicit function, no problem. Here's another one. X squared minus y. I'm trying to copy what I have in the notes in case you're following along. Again, y, if I plug in a value of x, I can figure out what y is, but it's not y equals an express function of the variable x. Of course, I could solve for that. So again, both of these cases are implicitly defined as they are now, but they could be solved to be explicit functions. But what about this one? There's no way to solve that for y, because there is no way to put these together. So this is a case where you could, and this is one where you would have to use numerical methods on the calculator. It's not one that we can compute even by hand. But this is an implicit function that cannot be changed. The thing that's interesting is that I don't have to be able to put it in this form in order to find the derivative. So let's take a look at how we're going to do that. Let's review a little bit of chain rule. Because chain rule is really what implicit differentiation is going to be all about. So remember our chain rule. Chain rule says that if you have some function, an outside function with an inside function, that its derivative, if I dx this thing, and take the derivative with respect to x, which is the most inside, then I can write the derivative of the outside times the derivative of the inside. This will just have an x. This will have whatever that inside function is. Okay, so another way to think about that then is I could write this function here, I could write this as d e d I. I know that seems a little weird, but I'm actually not taking the derivative with respect to x, right? I didn't put x inside, I put I inside. So I'm really taking the derivative of this outside function with respect to the inside function. And then this one is our regular one that is relative to x. So how does that help us? Okay. Let's look at one more example, kind of to lead up to where we're going. If I want to, if I have y equals x cubed, that's x cubed, and I want to find the derivative, I want to find y prime. Really what I'm doing is I'm going to take the derivative with respect to x of really the entire equation. And let's look at how I might think about that. So d dx of y equals d dx of x cubed. Okay, taking the derivative with respect to x of x cubed, that's a power rule. I know exactly what to do. That's just 3x squared. Taking the derivative with respect to x of y, I don't treat that like a power rule at all. So this I would just write dy dx. The variables don't match. I can't do a derivative. I can do the derivative over here because I'm taking the derivative with respect to the same variable. Over here I'm not, so I can't do the derivative, so I just write what it is. Okay, so putting that all together, so the key is to really look for that with respect to variable. I'm going to lay out a table, and then I think it'll be much more clear kind of how this gets put together and how it relates to chain rule. So if I wanted to take the derivative with respect to x of x squared, I would get for an answer 2x. If I want to take the derivative with respect to x of y squared, the variables don't match, so how do I do that? Well, let's think about this. Let's consider this to be an inside-outside function. Let's just rewrite it. Here's our inside function, and there's our outside function. Inside function, outside function. So the derivative of the outside function is 2 times the inside, times the derivative of the inside function. What's the derivative of y with respect to x? That's just dy dx. Okay? So I'm treating this like a chain rule, where the inside function is no longer x. Here it's x, straight power rule. Here it's not x. So I treat it as a chain rule situation, a composite. I handle the outside function like I did over here. So the 2x, in this case, becomes 2y, because this is the derivative of the outside times derivative of the inside. But here we put the inside back in. So that's what I've done. So let me do another example, and I think the pattern will be more clear. All right, so let's look at d dx of x to the 1/2 versus d dx y to the 1/2. Here, with respect to x, the variables match. I just do a standard power rule. So 1/2, exponent comes down, x to the negative 1/2, 1/2 minus 1. If I wanted to, I could write it as 1 over 2 square root of x. What about over here? Variables don't match. So because they don't match, I need to treat this like a chain rule. So I have my inside and my outside. So I'm going to do the outside function, 1/2 to the minus 1/2, just like over here, times the derivative of the inside function. Derivative of y with respect to x, that's just dy dx. Okay? So in the end, I would get 1 over 2, and what goes in here? Remember, it's the chain rule, so the inside goes in. So square root of y. And sometimes we will write dy dx as y prime. It's just a little bit more compact, and when we get to needing to move around some variables, it's a little bit easier to deal with. Okay? So derivative of x squared is 2x. Derivative with respect to x of y squared is 2y. And again, let's write this way, 2y, y prime. Derivative of x to the 1/2 is 1/2 x to the minus 1/2. Derivative of y to the 1/2 with respect to x is 1/2 y to the minus 1/2 dy dx. So let's do one more example. I'll leave that one up there. d dx ln x versus d dx ln y. Variables match, 1 over x. Variables don't match, 1 over y, times derivative of the inside, y prime. So I'm going to rewrite all of that kind of in one concise table. I think that will help you see the pattern more easily. Let me do that. So we're going to have d dx of x squared is 2x. d dx of y squared, 2y prime. d dx x to the 1/2 is 1/2 x to the minus 1/2. d dx y to the 1/2 is 1/2 y to the negative 1/2 y prime. d dx, we're going to do ln x. Ln x, 1 over x. d dx ln y, 1 over y times y prime. So 2x, 2y. 1/2 x to the minus 1/2, 1/2 y to the minus 1/2. 1 over x, 1 over y. The difference is, this is handling the outside function. I have to multiply by the derivative of the inside function, which is y. So that's why I consider implicit differentiation to be chain rule. If you just always remember, if the variables match, straight derivative. If the variables don't match, do the derivative and then multiply by your y prime to be the derivative of the inside.